So we're going to finish up this unit with a discussion of cost functions and regularization. Complex models can overfit training data and fail to generalize. Regularization improves these models by adding a penalty that discourages overfitting. Encourages simple models by shrinking coefficients. And it's widely used with regression and classification models. So ridge regression adds a penalty proportional to the sum of squared coefficients. J of beta equals loss plus lambda times the sum of beta squared. So lambda controls the strength of regularization. It doesn't set any coefficients to 0. It just shrinks all of them, and it helps when predictors are highly correlated. Lasso adds a penalty based on the sum of absolute values. Unlike ridge, lasso can shrink some coefficients to exactly 0. It acts as an automatic variable selection technique. And usually when we select only a few variables are relevant. Elasticnet is a hybrid between lasso and ridge that balances sparsity and stability, preferred when features are correlated and the model selection is also desired. It's tuned using cross-validation, choosing both a lambda 1 and a lambda 2. So how do you choose lambda? Cross-validation. There's this old joke that if you fall asleep at a machine learning conference, and you have to ask a question, knowing nothing about what happened during the lecture, you can always say, how did you choose lambda? Because there will always be a parameter named lambda, and there will always be some tuning. And if you ever have to answer and you've forgotten everything, you can always say, I chose lambda via cross-validation. So too small leads to overfitting, too large leads to underfitting. Cross-validation is commonly used to find the best lambda. Try a grid of lambda values, evaluate error via k-fold cross-validation, and find the lambda star that minimizes the validation error. So, summary of the toolbox: ridge slings off coefficients, lasso creates a sparse solution with fewer variables, Elasticnet combines strength of both, and cross-validation provides model tuning and regularization parameter selection. To evaluate model performance, you generally split the data into training sets, testing sets, and validation sets. Training sets are for fitting model parameters, validation sets are for tuning hyperparameters, and test sets are for assessing the final generalization. So performance can vary based on how the data is split. You use cross-validation to get more reliable estimates. There are several types of cross-validation, including k-fold cross-validation. We split the data into k-folds, train on k-1 and validate on 1. You repeat this k times and average the error. Leave one out. Cross-validation is an extreme case of k-fold where k equals n. It's precise but computationally expensive, and stratified k-fold preserves the labor proportions of each fold, and it's important for classification problems. Thank you, and I hope you have a great day.